Here we're going to solve the velocity of a ball falling under the influence of air resistance. So what we're going to be given is a ball of mass m, and we'll be falling with an initial velocity at t equal to 0 of 0. It will be falling under the influence of gravity of the Earth, so we'll just take g as gravity, 9.8 meters per second squared. And we will take the force of air resistance, which I'll call F sub d, to be simply minus some constant k times the velocity of the ball. And what we're going to find will be the velocity of the ball at some later time t as it falls under the influence of both gravity and air resistance. And obviously we're going to use Newton's second law. So the first thing we want to do is draw a free body diagram. There is our ball. It will have two forces acting on it. It will have the force of gravity down, F sub g, which is simply m times g. And it'll also have the variable force of air resistance, F sub d, which is equal to minus k times v. Now, because it's going to be falling and accelerating downward, I am going to basically take x down to be positive. So gravity is a positive force acting downward. Air resistance is a negative force acting upward. Those are the only two forces I need to worry about. So now I can just write down Newton's second law, the net force, which will just be the sum of gravity right here and air resistance right here. So it'll be mg minus kv, and that simply equals mass times acceleration. Now, this looks like a simple algebraic equation, except the acceleration is not just a parameter, it is in fact the derivative of the velocity. So what I really have here is a differential equation. So let's write that down. We have basically mg minus kv equals m times dv dt with the initial velocity equal to 0, and we want to solve that for the velocity as a function of time. So we have a differential equation. First thing we want to do is rearrange this to collect terms together. So what I'm going to do is divide both sides of the equation by this expression, and then multiply both sides of the equation effectively by the differential of time. So what we're going to have is basically m dv divided by mg minus kv, and that's going to simply equal dt. Now I'm going to do something that might look a little odd, but I'm going to multiply both sides of the equation by minus 1. I'm going to do that largely because I'm going to distribute this minus sign down on the bottom, so I have a positive velocity. So this, therefore, is, and I'm also going to divide the entire equation by m, or multiply both sides by 1 over m, to get rid of the mass on the top and get rid of the mass on the bottom, and collect my constants together. So I'm going to rewrite this thing, and it's going to end up being simply dv divided by k over m times v minus g, and that equals minus dt. Now what we're going to do is integrate both sides of the equation. And we have to specify our limits of integration. Well, we know our initial condition is we're starting with the velocity equal to 0. So I'm going to integrate from time t equal to 0 and my initial velocity, which was 0. And I want to find my velocity at some later time t, so I'm going to integrate this to some time t, and my velocity will be the velocity at time t, which is v. Now I know this is going to look a little strange because I have right here a variable of integration, which I have called t, and a variable of integration right here, which I have called v. And my limits, unfortunately, also include a time and a velocity. To clarify that, what I'm going to do is simply write the variable of integration with a script, and the t variable of integration will also be a script, and the printed letters will be the limits. So we're going to rewrite this to be the integral from 0 to v of dv divided by k over m times v minus g equals the integral from 0 to t, the minus sign out in front, times dt. Now we don't have the slight confusion of having the various symbols being used differently in different places. Now, this side of the integration over here is trivial because we're just integrating dt. This right here will just be minus t evaluated at 0 and t, which is just equal to minus t. So that side is simple. The side that's not so simple is this side right here. So we need to evaluate that integral. And to do that, we'll rewrite that on a new page. So we have the integral from 0 to the final velocity of dv divided by k over m times v minus g. Now that kind of looks like, although it's not, the integral of dx over x. X is sort of v, but on the bottom I don't quite have x. I have k over m times v minus g. But I'm going to do a substitution so I can make it look like this, because this right here will give me the natural logarithm of x. So what I'm going to do is I'm going to call this right here my variable x. So x is going to equal k over m dv, oh excuse me, it's not dv, that's just v, v minus g. Now I can take the differential of this, dx will equal k over m times dv, or dv will equal m over k times dx. Now what I want to do is find out if I'm going to take and rewrite this integration in terms of x rather than v. I need to also evaluate what is x at the limits of integration. Namely, when v equals 0, what is x? And when v equals, well, v, what is x? So my limits of integration will be, we will start at the beginning, x at t equal to 0 is simply minus g. We simply say this v is 0 and we get minus g. The final, the top integration, will equal, well, k over m times v minus g. Now I just need to substitute the limits of integration in, substitute this in, and substitute this in, and we end up with our integral looking a little bit better. We now have the integral of just m over k times dx divided by x. That's actually kind of messy. Let me rewrite that. It is the integral of k over m times dx divided by x, and our limits of integration are from minus g to k over m v minus g. Now notice, now all the complications which used to be in the integrand are now in the limits. So my integral actually is fairly simple. Let me write the constants out first. It's k over m times the integral from minus g to k over m v minus g. That's where all the complications are, of simply dx over x. And that is just equal to k over m times the natural logarithm of x evaluated at my two limits. And now all we need to do is plug them in and evaluate them. This is getting a little messy. So what we have is k over m times the natural logarithm of x evaluated at minus g and at k over m v minus g. And that just equals k over m natural logarithm of this ratio, k over m v minus g over minus g. Now, the minus g is kind of annoying because it makes it look like we're actually taking a logarithm of a negative number. So I'm just going to take and put the minus sign and distribute that out. Remember, all of this ended up equaling, if we go back to the other side of our equation, all of this ended up equaling minus t. So what I have, this is equal to minus t. Now I want to solve that, because we're not done yet. This is a lot of algebra now. I want to solve that for v. So I'm going to take and multiply both sides of this equation by m over k. That cancels this out. Then, of course, what I want to do is exponentiate both sides to get rid of the logarithm. So I end up with minus k over m times v plus g, all divided by g, must equal e to the minus m over k times t. Now we're going to take and divide this out, and we end up with minus k over mg times v plus 1 equals e to the minus m over k times t. Now I'm going to bring this to this side of the equation and the exponential to the other side of the equation. And we end up with 1 minus e to the minus, back here, e to the minus m over k times t is equal to k over mg times v. K over mg times v. Then I just need to multiply the whole nonsense by mg over k. And we end up with what we wanted. The velocity is mg over k times 1 minus e to the minus m over k times t. And there's our final answer. The question is, does it make any sense? Well, let's go back to the very beginning. Here we have two forces acting on this ball. The drag force will increase in value as the ball speeds up. And eventually, it will get big enough so that these two forces are equal. At that point, the net force will go to 0, and the object will stop speeding up. So, therefore, I would expect the velocity to reach a terminal value. And that'll happen when these two are equal. So when kv equals mg in magnitude. They'll be opposite in direction, that's what the minus sign means, but they must be equal in magnitude. Or the final terminal velocity should be mg divided by k, which means I expect the velocity to increase and asymptotically approach a final value of mg divided by k. Is that what my answer tells me? Well, here's my mg divided by k. This is what I found to be my terminal velocity. And as t gets big, e to the minus something times t will go to 0 as t gets big. So that'll go to 0. So then I'll have 1 minus 0. So in the limit, this will in fact approach my terminal velocity, which is exactly what I expect it to be. Okay, so the end point reaches a terminal velocity. What about what I wanted? Is v0 actually 0? Well, I plug in t equal to 0, e to the 0 is 1, 1 minus 1 thankfully is 0, so yes, that checks out. The initial velocity is in fact 0. So I have the correct initial, the correct final velocity, so therefore this actually is my final answer. What does that look like graphically? Well, if I'm going to plot this as a function of time, and here's my velocity, I'm going to end up with something that is going to exponentially approach the value of the terminal velocity. So this right here would be mg divided by k. That's this term. And I'm going to start with velocity equal to 0. It will look something like this, where it asymptotically approaches the terminal velocity. Initially down here, it will start speeding up. Because the air resistance is small, gravity is large, it will begin to speed up. In fact, very close to the origin, it will look pretty much like free fall. However, right here we see air resistance getting very large, and we are reaching our terminal velocity. And this right here will be close to free fall. And that's our final answer.